Let's say we have some Boolean function, and the function has 3 inputs, A, B, and C, and it has 1 output, Z. We can define this function using a truth table, and of course we can implement the logic defined in the truth table as a circuit. But what if we have more inputs and a more complex function? Standard practice would be to simplify the logic, perhaps using a Carnot map, and that's easy enough to do with only 4 inputs, but what about 5 or 6 inputs? To give us an idea of where I'm going with this, I need a control system for the RISC-V CPU. It'll need to make decisions like whether to add or subtract, whether to write or read memory, or should we write the ALU result back into the register file, and other decisions around the CPU as well. All of these decisions will be based on the opcode and the function codes, and these are inside the instruction. The opcode has 7 bits, the funct3 code has 3 bits, and the funct7 code has 7 bits, although we'll only need to look at bit 5 of the funct7 code since the other bits inside of there are not used for the RV32I spec, which is the one that I'm implementing for this CPU. So that's a total of 11 inputs to the control unit. And we have numerous control outputs to the rest of the CPU as well, and I'm only showing just a few of those here. I don't want to work with an 11 input K-map. Not only is this impractical to use, but for my purpose, I'll almost definitely want to redesign the logic at some point. In fact, probably at many points. I don't want to have to design a perfect solution for the final CPU on my first try, so I'll be using a ROM as a programmable logic unit. The ROM that I'll be using is the AT28C64, and this is the same chip that I used for the instruction ROM. I cover the I/O and timing for reads and writes in a lot more detail in that video, so I'll keep it pretty high level here. If we have a look at the pin configuration, the key points are that we have 13 bits for the address. I'll only need 11, so I'll tie the upper 2 bits low. We have the various enable pins for setting read and write modes, and we have the 7 bits of I/O, and the other pins we can ignore. So I'll be connecting the opcode and func codes to the address, and then by programming the ROM with the data that we want to output for each possible input, we'll have a reprogrammable lookup table for the control unit, and when we set the ROM to read mode, the I/O will be outputting the control signals. I have here the control module that I developed in the previous video, and if you watched that one, you'll recognize the clock circuit and the prescaler down the bottom left here. But I also have these 2 sockets, and they're for the ROM chips that I'm going to use for the control itself. This board fits into the other 2 boards that I've got here. So this is the instruction ROM. So these 4 chips up here are the ROM that's going to hold the program that we're running. And then the next board down here decodes the instruction. So it will figure out what type the instruction is, what the registers that need to be referenced, what the immediate value is, and so on. And then those signals come down to the control module. So that's how we're getting our opcode and funct codes into the instruction ROM to generate the control signals. The outputs of the control are indicated here with some LEDs, so we'll be able to see if our ROM configuration is implementing the right signals by programming in some instructions and having a look to see what control signals are coming out on these LEDs. To program the ROM, I'm going to use an Arduino. Now this is a bit of a rat's nest, but it should do the job. Now the Arduino by itself doesn't have enough I/O to program the ROM chips that I'm using. I've got 13 address lines, 8 I/O lines, and a few control signals, so I don't quite have enough for that. What I'm doing instead is using 2 Arduinos, so one as a master and one as a slave. The master is the one on the right here, and that provides the data, and it sends the address to the slave, which is the Arduino on the left. And I'm just using the Arduino wire library to communicate between the 2. Of course, this would have been easier if I had a shift register or I/O expander in hand, but I don't, so this will have to do. Now, I confess I was a little lazy, and the code here may have been developed with some AI assistance. But starting with the slave sketch, we have a pinout nicely presented, thanks AI for that, and you'll see that we use a mix of digital and analog pins for the address outputs. It's useful to note that the Arduino analog pins can actually be used for digital I/O as well. You can also see that we're using the hardware I2C pins on A4 and A5, and then the wire library to communicate between the two boards. In setup, we're just configuring the address pins as outputs and preparing the I2C communication. The loop does nothing since the hardware interrupt will call the receive address function whenever a message is received from the master, and the receive address function just reads in the two address bytes, combines them into a 16-bit address, and then sends each one of those bits one by one to the address pins. And that's it, simple enough. Now over to the master sketch, we have the pinout once more, but scrolling down a little, I've added a heap of constants to help construct the ROM data. First of all, I've got a list of the opcodes and func codes, and these will be used to construct the ROM address, since these are the inputs to our control function. Then I have each bit of the control specified, 16 bits in all, 8 on each ROM, and these will control things like the ALU operation, the sources for the ALU, or whether we're moving to the next instruction or jumping somewhere else in the code. And finally, we have an array of data to store in the ROM. The first column has the address, which is constructed from the opcodes and func codes that we saw just a moment ago, and the second column constructs the control signals needed by combining various bits. For example, to subtract, we need to select the ALU add submodule, and that's the one that I built in an earlier video. We need to specify that the module should subtract. We need to tell the ALU to get its inputs from the registers and to write its result back into a register. And finally, it should move on to the next instruction when it's done. The rest is the code that was mostly generated by my AI friend. We set up the control pins and serial comms again, similar to the slave, and then iterate through our carefully constructed array of control signals. Since the AT28C64 ROM chip only has 8 bits of I/O, I'll need to program 2 chips, and so I can set this upper flag to choose between the upper and lower byte. So I'll run the program once with this set to upper, and then once again with it set to lower, and it'll choose the appropriate byte from our data. The write to ROM function sends the address to the slave and then writes each bit of the data to the I/O pins one by one. Alright, let's upload this to the board and have a look on the serial monitor. I just need to change the baud rate. I think it was, there we go, 115200. Alright, and let's have a look at the output. Looking at the output here, I can see that it has attempted to write, but the readback is not showing the correct values. So something's gone wrong here. Not a single error. That's incredible. Wow, okay, that was more problematic than it should have been. I'm not even sure which change I made fixed the problem. I find with these chips that timing can be a real issue. Even if I follow the timing specified by the datasheet, it doesn't work reliably. In the end, I increased a few of the delays and added in 1 or 2 more, and that perhaps solved the problem. Now I've loaded the upper and lower bytes onto these 2 ROM chips, and it's time to put them into the control module. I have a program running on the test board that reads in the clock, and every time it gets a rising edge, it steps through the 9 addresses of the test program that's loaded on the instruction ROMs. But again, that doesn't look right. Control signals that should be showing are not. So again, I'll need to do some debugging. Well, at least this time I know exactly what the problem was. The test board uses MCP23017IO expanders, and the library that I'm using for those allows me to set all the I/O as an input in one function call. This is really important since we don't want some other part of the circuitry trying to set a pin as, say, 5 volts, while the I/O expander is outputting 0 volts. But that's exactly what was happening. The ROM was trying to set the control while the I/O expanders were also trying to set them. Not good. Hopefully no damage done. But once I've forced all I/O pins to be inputs by default, the ROM was free to output whatever it wanted on those control lines. So this seems to be working. If we look at this instruction, it's a subtract operation, we can see that it's selecting the ALU control bit 3. ALU control bits 3 and 4 select which ALU module to use, and with bit 3 set and bit 4 off, this will select the add sub module that we built previously. We can also see that the sub bit is set, and so we're doing a subtract. So that all looks correct. The next instruction is a load word instruction, so reading from memory. Again, we're selecting the add sub module, and this is because we need to calculate the memory address. And we do that by adding a register value to an immediate value. And so the B source control bit, that is indicating that we want to read the immediate value into source B of the ALU. And the RD source control, that indicates that we want to write the value that we read from memory into the destination register. So these are all as expected, and I'm going to call this working. This is actually pretty exciting. There's only one thing left before the CPU can execute a command independently without needing the test module and the Arduino to drive it. We just need a program counter to store the current instruction address and to decide what instruction to execute next. And that's what I'll be building next time.